Okay, so here we have a problem very similar to what we have seen in chapter 16 with our weak acid dissociation, weak acids, weak bases. The main difference here is that now we prepare what we call a buffer solution by adding a small amount of our conjugated base to our acid. We added sodium acetate, mostly because they have to be in neutral form, so the sodium provides that positive charge to neutralize the negative charge of the acetate anion. However, for the purposes of our calculations, the sodium is just a spectator. So we start by looking at how much acid we actually have. We have 0.1 molar, so looking at the way we set up our ice tables, we have a 0.1 molar concentration. Initially, we don't have any hydroniums just yet, but our acetates, we actually do have a concentration. We have 0.05 moles, right here, per liter. So that gives us, we see the calculation down here, 0.5 moles per liter, that's 0.05 molar concentration. So basically the same number. After a set number of time, right, time passes, the concentration changes. I don't know about how much, but I know that for every one of my acid that gets consumed, one of each of my product gets formed, and I put them in the form of an X, until eventually I reach equilibrium by putting together my initial and my changes in concentration. I now have the means to create my Ka expression. I have it right here. 1.8 times 10 to the minus 5, that's the acid dissociation constant for acetic acid. And then I have what I obtained from my ice table. We make two assumptions, or actually just one assumption in two cases, and that is that the change in concentration for both the acid and the conjugated base is very small compared to the initial concentrations. That's what we have right here. 0.05 plus x is about 0.05. 0.1 minus x is about 0.1. That makes our lives a lot easier. We have right here the simplification giving us x as 3.6 times 10 to the minus 5, which is the concentration of our hydronium, which we then plug into our pH expression right here at the bottom to give us a final pH of 4.44. Now what happens, we have here a second example that kind of ponders what happens when we prepare a buffer solution and we try to neutralize it. In our case, we prepared a liter of buffer with a 1 molar acetic acid and 1 molar sodium acetate. But now we added 0.1 moles of sodium hydroxide. As you guys know, sodium hydroxide, a very strong base, will neutralize my acid. The chemical equation we see right here in the middle is a neutralization, so that means that my acid is going to get consumed as I add my hydroxide. Water doesn't participate, so I can just ignore it, and then my acetate gets formed. I get added as I add my base. Now, and here's the challenge here. For every mole that I add of my base, I neutralize one of my acids. So I added 0.1. That means that my concentration after I added that is going to be reduced by that same amount of the NaOH that I added. So 1 minus the 0.1, right? 1 minus the 0.1 gives me that 0.9. And then all of the AOH gets consumed. For the acetate, it's quite the opposite. For every one of the acid that I consumed, I form one of my acetate. So it would be 1 plus 0.1, giving me 1.1. That ratio I plug into my Henderson-Hasselbach equation to tell me what is the final pH. I use the pKa, which is the pX type version of my Ka value for acetic acid, plus the concentration of my weak conjugated base over the concentration of my acid. And that's it.